And of course, if you ever talk about it in class, you're talking about it to the people for whom it's not an issue. All right, today we're covering NFAs, which means that we need to start with a conversation that I started last time talking about non-determinism. So non-determinism is a very interesting concept in theoretical computer science that may not be hugely theoretical for too long. So what's nice about determinism is it's what you've completely interacted with in terms of the programs that you've written, the way that you have been taught how to think about solving problems. Determinism basically means that if you have all of the information, you can 100% for sure determine what the next step is going to be, or the next state is going to be. In a DFA, for instance, you know what the next character of the string is going to be, and as you define that DFA, as you write it, as you come up with it, or even if you're given one, you know exactly what there's only one possible transition from where you can go next. Given that the state is in, given that you are moving to the next state, there's only one possible transition from that state consuming that input character. So every program you've ever written is deterministic. You know the state of your program. So all of the variables have values. They don't have multiple values. Anything that's defined has a value, even if that value is null. But there is one and only one value for every variable in your program. Given the next line of the program, you can deterministically determine what the next state is going to be in the program. For every variable that is currently part of your working state, you can determine what value that variable is going to have by the associated transitions of applying that instruction to the environment. So an example of determinism that I really like to use, something like write a program that guarantees you will crack a password of 6 characters through brute force. You know the password is exactly 6 characters. And let's say for the sake of this problem, that legal characters are lowercase letters, uppercase letters, and digits. So no symbols are allowed in your password. So the first question I have for you is, how many attempts will it take in the worst case? You could be able to guarantee that we're going to crack this password within how many attempts? An expression is fine. You don't necessarily have to give me an exact number, but how would we define this expression for how many attempts it would take in the worst case?
To the number of characters minus 1 and something in 6.
Good guess. But not quite right. So characters in the 6. Yes. How many possible characters do we have? We have 26 possible lowercase letters, 26 possible uppercase letters, and 10 possible digits. 62 to the 6 would get us there. So I can write this out longhand as 62 times 62 times 62 times 62 times 62 times 62. And this basically says that this is all of the possibilities for the first character. So we have A through Z, A through Z, and 0 through 9. And it's going to be the same for each one of these characters. And you can see that if you were to draw kind of arrows between these, you could have here, the first 2 characters would be AA. Here, the first 2 characters would be AB. Here, the first 2 characters would be lowercase a, capital A. And you can do the same thing for every possible connection between these two. You could continue to do this for every one of these, and each one of them would represent a path, kind of through this visual diagram, how many paths would there be? And the possible number of paths is 62 to the sixth, and that would be every possible password of 6 characters that you could generate. If there were fewer than 6 characters, you'd have fewer 62s. If there were more than 6 characters, you'd have more than 62s. If we allowed more characters, each of these 62s would be larger. Fewer characters, each of these 62s would be smaller. So now how would we actually write the program that goes through and calculates this? Or at least a bunch of for loops. Whenever you see kind of this multiplication, you'd have a nested loop of some kind that says, you would have a sextuply nested for loop that says, for every character, for every character, for every character, for every character. Try whatever the current character happens to be. So it would start with lowercase a, all of them, and then it would slowly go through and hold the first 5 constants, manipulate and change all of the last character. Then it would move this character from lowercase a to lowercase b, try all of these again, which is how we get that 62 to the sixth. It's nice and brute force, but it's deterministic. Does everyone see how this is deterministic? If no matter how we wrote this program, there would be some sequence of way of figuring out all possible paths through this system. So let's discuss how this problem changes if we think about it non-deterministically instead of deterministically. So in non-determinism, we get, instead of having a next step, a next instruction, we get a set of possible next steps. So we explore each possible successor state in order. We look at one. When we return from that, we look at the next, and it would be kind of a depth first search, or you could also phrase this in terms of a breadth first search, in terms of searching the possible state space. If you recall back to algorithms and the fun of searching through graphs or trees in algorithms. In non-determinism, we look at all possibilities, and whatever the correct one happens to be, we select that one. We're able to look at them all in parallel. And basically, one possible way to think about it is how long does it take for you to verify the correct answer? So of all possible passwords of length 6, I say that my password is D capital Z 3 4 9 B, lowercase b. Great, that's my password. How long would it take for you to verify that that is my password or not? You already have my login, my username. So to tell me, yes, that is your password, or no, that is not your password. Just one operation. It would take you 6 enters of some character. It's based on the length of this string. You would, however many possibilities, there were 62 possibilities here, right? But if I tell you what my password is, how long does it take me to verify that? Of the 62 possibilities, I just select the correct one. So we're moving down from searching to verifying. So determinism can be thought of like searching, non-determinism can be thought of as verifying. You can also think of it as making a guess, and the guess that you make happens to be the correct one. Lots of different ways to really think about it. But whenever you have a branch like this, you just select the correct branch. An example of non-determinism is exactly what I just said. Write a program that verifies that a password given to you is the correct password. If we wanted to analyze the computational complexity, the order of determinism in this case. So I don't give you the password and you have to use brute force search. What computational order, what order are we in for this based on the length of the password?
I'll put down the question.
So you know that we have orders like linear, quadratic, cubic.
Whatever that word is for six.
Yeah, so it would be, if we had a password of length 6, if we wanted to do this in general, we would have like the number of possible characters to the length. If the length isn't constant, then this is exponential. Or it represents some variable of the potential length of that. If this length is held constant, then yeah, it's some polynomial based on whatever constant that length happens to be. Sometimes we end up with something that says, you know, the password is 20 characters or less. Sometimes there is no upper limit to the size of a password. So this does vary a bit, but I'm gonna go with this is basically exponential. If we don't know what the length of the password is, we have to check all passwords of length 1, all passwords of length 2, all passwords of length 3, until we find it, with no real upper bound. What is the computational order for non-determinants in this case?
Be constant.
It would be constant if the password was length 1. I now say my password is length 10 billion. Does it still take the same time to verify a password that is length 10 billion? It's like 5. Yeah, it's linear based on the size of the length of the password. So going from determinism to non-determinism, we've moved from something that is potentially exponential in complexity to something that is linear. We know exponential is computationally infeasible, and we know linear is extremely efficient. So there are some really interesting theoretical results when you think of, okay, well, obviously determinism and non-determinism are different problems, right? You can't apply either determinism or non-determinism to a problem. But if we could find some way to convert a deterministic algorithm into a non-deterministic algorithm that just ran and verified, chose the correct path, or could look at all paths in parallel, then we would get a massive computational advantage. And things like password cracking could actually become computationally feasible, which would kind of break security of the internet and everything else we hold dear. So we kind of hope that this isn't going to happen, but takes a single attempt. We're going to take a slight break from this concept of non-determinism and go back into kind of a how can we make an automaton that is non-deterministic in nature? What do we need to do to our definition of a deterministic automaton to turn it into a non-deterministic automaton? And we'll find some interesting results when we analyze what this non-deterministic automaton can do compared to a deterministic automaton. Any questions about non-determinism before we do that? Is the concept clear? So just like before, we're going to have a book definition of an NFA. Whenever I say NFA, I mean non-deterministic finite acceptor. So just like a deterministic finite acceptor, it looks defined to be exactly the same thing. It's defined exactly as a DFA is, with the exception that the transition function, delta, is now, instead of just being the number of states across the size of the alphabet, which is what we had before, we now need to add this new symbol, lambda, to it. And we'll get into exactly what this lambda does, but it tells us that there are going to be, in the end of this, 2 to the number of states, number of possible transitions. That's a bunch of technical garbage. So let's try to make this clearer. Let's just look at the differences. So if we know and understand what a DFA does, how is an NFA different? Difference number 1, we're going to allow a lambda transition, which is a transition between 2 states that does not consume an input character. You can now teleport. You were in Q1. If there is a lambda transition between Q1 and Q3, you can just teleport there. You also do not have to. It becomes a choice whether you do that or don't do that. And as we know about non-determinism, whenever there's a choice, you just do the right thing. We can also have multiple possible transitions out of one state that consumes the same input character. So in a DFA, we were in a particular state, we consume the character A. There is only one possible transition out of that state that consumes that character. In an NFA, there can be an arbitrary number of them. There can be 0. There can be 8. There cannot be infinite. But as long as there is some constant. So this is the 0 part. You do not need to specify every possible transition out of a state. If there is no possible move that we can make consuming that input character, think of it as an immediate reject. So we can stop early if there is no possible transition out of a particular state that consumes a character. So let's take a look at an actual NFA. So this has some of these differences. Where in here is there an aspect of one of these three things that is different than we allowed in a DFA? Spot the differences. Upper division computer science style. Yeah.
There's a lambda transition from Q0 to Q2.
Yeah, so lambda transition here, so you just label that edge with the character lambda, and it basically is a free one-directional teleport from Q0 to Q2. What else? Any other differences?
Q2 doesn't have any out.
Yeah, there's nothing coming out of Q2. So if we end up in Q2 and we want to consume a 0 from the input string, we automatically reject. What else? Yeah.
Q0 goes to Q1 or Q2 if you have a 1.
Mm-hmm. So if we have a 1 from I think it's a 0 from here, right? There's no other multi-edge of a 1. But if we're in Q1 and we read a 0, we now have two options of where to go. We could go to Q0 or we could go to Q2. So one important aspect of this is we are going to accept a string if there exists a path in the NFA from the initial state to a final state. It doesn't have to be all possible paths. It doesn't have to be most possible paths. There might be 10,000 possible paths through the NFA for a particular input string. As long as at least one of them ends in a final state, we accept. Does that make sense? Like for instance, the string 1, 0 starting at Q0. We read a 1. Well, first we have two options of what we could do. We could either move to Q1 or we could lambda transition and attempt to read a 1. One of those results in immediate failure because there's no 1 coming out of Q2. If we read this one, we end up in Q1 where we're still alive and moving through this string. So great, we're gonna do that, kind of ignore this because it leads to failure. Now, we want to read the 0, and there are multiple ways that we can branch from Q1. We can either move to Q2, or we can move to Q0. Regardless of where we are when we do this, we're done with the string. So is there a path that ends at a final state? Yes, the path through it are the transitions Q0 to Q1, consuming the 1, and Q1 back to Q0, consuming the 0. Even though there are other paths, multiple other paths through this NFA, as long as at least one of them ends in a final state, we accept the string. Yeah.
So for this one, for example, the only possible strings would be 1, 0. then 1-0, then 1-0, just repetitions. of-
Yeah, this is not the most intelligently designed automaton. It's just meant to be simple and explain these differences. It doesn't really do anything interesting. It's arbitrarily complicated for no reason. The state Q2 is kind of useless.
So with this, so since a NFA, you don't have to show every possible transition, or you don't have to show a pathway that doesn't exist. Or at least can't be used. Would this be a DFA then?
It is not a DFA because the lambda transition is not allowed in the DFA. There's multiple zeros,
Yeah.
not allowed, and the fact that we don't specify what happens in Q2 on any output is also not allowed. So it violates all three of these. None of these are allowed in a DFA, but all three of them are allowed in an NFA. Great questions.
So is like, if you have a state that has no penalty you can go from, is there any use for that, other than just using this trap state?
That basically would be considered to be a trap state, but in an NFA, you don't need a trap state. Trap states are useless. Because if you don't specify the transition, we automatically reject. So yeah, trap states are really only useful in a DFA. The fact that we even have this is completely unnecessary. We could get rid of Q2 and every transition into Q2. And it would be exactly the same in terms of what language it accepts.
So it only really exists just this not really.
It exists to show you the differences between DFAs and NFAs. Yeah, it's not my favorite diagram in terms of the usefulness.
Just like, how is this state that you can't move out from school? Besides just being able to stop.
Yeah, in general, you wouldn't want to include it in the NFA. Because it's always going to be equivalent to that same NFA with that node and all paths into it removed. Great question. So I throw this concept at you, and maybe it's kind of intellectually interesting, but you might ask, what's the point? Why would we care to study this intellectually interesting idea that doesn't seem to have a point? Let's talk about why we care. So, of course, we've talked about how computers are fully deterministic. Algorithms that we can write are fully deterministic. What value is there to non-determinism? The answer is that problems, significant numbers of problems out there, difficult problems, have easy non-deterministic solutions like this password cracking, and difficult deterministic solutions, if you actually have to find the answer to it. So that leads us to be able to say and find some really interesting results. So we can show that if you start with an NFA, you can create a fully equivalent DFA. Intriguing. What this means is that the actual computational power given to you by an NFA is not greater than a DFA. It doesn't solve any more or different problems. It solves exactly the same problems. But sometimes constructing an NFA is significantly easier than constructing a DFA. So if we had some way to represent a complex problem as a simpler problem that has an equivalent complex solution, does that mean that we could write a non-deterministic algorithm that is equivalent to every deterministic algorithm? If we could find a way to write a non-deterministic algorithm, that would simplify our lives and allow us to solve many, many more problems in an amount of time that is actually useful to us and we will be alive to see the result for. If you've talked at all in any of your classes about how difficult it is to solve an exponential problem or a factorial problem, how quickly those scale and become useless to even consider. So as an example, we'll take search and backtrack algorithms. So optimizing a search and backtrack algorithm. If we could make an intelligent decision at every branch that said we are most likely to find the goal down this branch and not that branch, without exhaustively searching each of their state spaces, then we end up with a form of non-determinism. where we can make an intelligent decision at the current node. If a particular path leads to failure, you can backtrack and look at the next most likely choice. So it's kind of somewhere in between determinism and non-determinism. It's determinism with educated guesses. If we could use non-determinism, we could figure out how much work is required. Rather than actually just kind of, the cop-out answer in any algorithmic analysis is just using the worst case, because it doesn't take very much work to figure that out. But we get closer to the average case, or the intelligent case, if we can include some optimizations. Who is familiar with the P equals NP problem in computer science? One of you? Do we know what the P and the NP stand for?
Polynomial.
Polynomial, that is the P. Yep. What does the NP stand for?
Non-deterministic.
Yeah, non-deterministically polynomial. Open problem in computer science that will win you at least $1 million if you're able to mathematically prove this, one way or the other, is are these equivalent or are they different? We don't know. We have educated guesses, but no one has been able to mathematically prove this or disprove this. Which means that if we have a non-deterministically polynomial time algorithm for solving some problem, does a polynomial time solution exist for it? Deterministic. So deterministically polynomial, non-deterministically polynomial. Are they the same? Are they not the same? For all problems? We don't know. How would we find how would we fail to prove it? We just kind of need a counterexample, something that says we can't solve this problem in deterministically in polynomial time. We can solve it deterministically in non-deterministically in polynomial time. So the question basically, all algorithms that are solvable non-deterministically in polynomial time, able to be solved deterministically in polynomial time. Interesting open question. If you've heard of the class of algorithms called NP-complete, this is a class of algorithms where we have found a polynomial time non-deterministic solution. But we have not found a polynomial time deterministic solution. So the password cracking example that I just used is one such algorithm. The traveling salesman problem is a well-known NP-complete problem, where you have some graph. You have nodes, you have edges, and those edges have weights. The idea is starting at a particular vertex, you want to traverse and visit every other vertex in the graph and end up back where you started, minimizing the total distance that you travel. As the graph scales in complexity, this becomes something that we just cannot solve efficiently. We can solve it by brute force. It takes exponential time based on the number of vertices in the graph. If we can find a deterministic algorithm that can solve that in polynomial time, this is a class of algorithms where we have polynomial time conversions between all of these algorithms. So what's funny is we have, here is the traveling salesman problem. Just envision this as a node in a graph. There is a polynomial time, so some, how do we want to state this? N to the P, some actual value here for the polynomial conversion time algorithm into some other algorithm. I'm just gonna call this 2 because I mean, we can go. We can find the SAT problem, the 3-SAT problem. There are all sorts of actual algorithms in this class. But this graph has a bunch of, we can convert via some polynomial time algorithm into each one of these other algorithms. So as soon as we solve one of these algorithms in polynomial time, we use this polynomial time conversion algorithm. We solve this in polynomial time. We use this polynomial time conversion algorithm. We solve this in polynomial time. So we only have to find one solution to one of these problems in polynomial time, and we've proved that P equals NP. For at least the NP complete algorithms, everything that we add to this class. The security of the internet is based on P is not equal to NP. Everything breaks if P is equal to NP for NP complete algorithms. So that's really intuitively why we care about studying non-determinism, is eventually being able to state one way or the other that P is equal to NP or P is not equal to NP. The wrench that is thrown in this, and there's a really interesting video we can watch later this quarter if people are interested, is that we can prove that there are things in math that we cannot prove. Math is incomplete. Is P equal to NP or not equal to NP one of those things that is true that we cannot prove? There's no way to prove that. So there's just a whole bunch of we don't know with regards to this open problem. But hey, if you solve it, you're rich. Good luck. Questions on that concept or kind of just the why behind studying non-determinism? It makes our lives a little bit easier when we construct finite automata because we have these extra rules that we can use. So yeah, no proof exists, solve it, become a millionaire. Easy, right? We're going to study this whole idea about kind of the limits of complexity, the limits of what we could use a computer to do later in the course. At least a deterministic computer. Note that as you write a grammar, we also have some built-in non-determinism. Whenever we use an or in a grammar, we're stating if there exists a way to construct the final string from the grammar, then it's a part of the language. That's non-determinism. We allow it in grammars. It makes our lives easier when writing grammars. All right, we feel like we have an understanding of what an NFA is, the rules associated with an NFA. All right, let's get one group of 2 and one group of 3. Design an NFA for the following language. We have 2 definitions. We're going to union them together. And that says that if the string is a member of this language or a member of this language, then we accept. Only if it is a member of neither language should we reject. First of all, is the terminology of this clear? When I say a to the n, what does that mean? Yeah, some number of a's. So concatenating a with a with a with a at least 3 times. A string that starts with AB and then contains one or more n's. Sorry, one or more a's at the end of that. Remember that you can have linear transitions. You can have multiple paths out of a node out of a state with the same transition symbol. You can have no transition symbol out of something. That mostly prevents you from needing to use trap states. Have at it. Group of 2 here, and I guess a group of 2 here. Your choice about which group you'd like to join.
Then we need to find a state. There can't be exactly what's-
I think the language of purpose here that becomes a little bit more complicated as you try to make it a DFA. So think about utilizing those differences between DFAs and NFAs. And come up with a simpler solution that utilizes the power of an NFA.
The day there, that's good. One, two, three, so you can do that. So this has to be ABA, very good one, so ABA. After that, this can be as many as 7 months. No, it's not be like. Process. Follow this one with this.
Yeah.
But you just have three. Hey, and I was. Yeah.
Anyone have an answer?
I mean, I don't know that we don't take advantage of, the only NFAs that take advantage of having all legal frames.
Sure. Let me show you what I think is the easiest explanation to, or the easiest version of this to explain. It is not the most optimized version, but I see this and this is where I want to start. I see a union. A union basically means or, which tells us already that we can just branch. Given an input string, are we in this, the left-hand side, or are we on the right-hand side? But we're just gonna make 2 splits of Q0, one for the left-hand side, one for the right-hand side. We can just decide, make the right choice non-deterministically when we make that first, when we see that first symbol. So we're going to have a transition to a Q1 on an A, and the left-hand side says we need at least 3 A's. So Q1, Q2, and Q3 are all going to be the left-hand side. Now, we can make this a final state and loop this on an A. Right? That would be an NFA for the left-hand side. We don't need to define any transitions on B's. They would just lead to a trap state. Now let's focus on the right-hand side with a completely separate transition from Q0. So this language also starts with an A. So going to Q4, we're going to take advantage of the fact that Q0 in an NFA can have multiple transitions out of it with an A. That's allowed in an NFA. We know that. We need to then read a B. We get to Q5. We need to read at least one A to get to a Q3. So we have a couple options here. I'm just going to draw this as such. Q6 on an A that loops to itself on an A. So here we kind of have the left side language and the right side language. Does anyone argue that this does not solve this problem for some possible string?
It solves it, but can you make it a little simpler by putting like A and B on like a single string?
There are plenty of optimizations that we can make to this. Yes, that was going to be exactly my next point. What could we do to this to make it simpler? Sure.
So have Q0, go to Q1 with A, move back to Q0 with A or B, and then have it go back to Q1 again with A. So it has to do
Okay.
A or ABA in the beginning, no matter what.
Okay. I actually prefer to take one of Q1 and Q4 out completely, because we know that regardless, we're going to see that first A. So let's say that Q4 is just straight up not necessary, and we can make a transition to Q5 on a B. What else could we do?
Q, well, it's repetitive, but we could have like Q5 go to Q3 on the day instead of Q6, just get rid of Q6 altogether.
Yeah, when we see that we have two subsystems that are identical here, we can get rid of one of them. And we could say that we see this B, and now we need to see at least one or more A's. So why not lambda transition here? You could do that. You could also make this a B. That involves getting rid of yet another state, but I just wanted to show you that this is something that we could do to make this a little bit simpler. This tells us we can teleport from here to here and just read the extra A. But when you see this, you can sometimes get rid of this and just add the transition here on a B.
Does this one also work? Right here?
Not quite, because what happens with the string? ABA,
A, B.
lambda. Yeah, you're right. That may very well work. There are a lot of interesting solutions for NFAs. It's really hard to see all of them right away. Yeah, at least at first glance, I buy it. I'd have to look at it in a lot more detail to see if I could find a counterexample, but I think that might be solid. The only concern I would have is there any other way? I guess, yeah, with an A. What about a single A? Yeah, a lambda transition, there's a way to accept for a string that shouldn't be accepted. So it's close. Close. So lots of ways to think about this and think about optimizing it. One more for you. see if you can now make use of some of the elements of NFAs. For A to the n is odd, union b to the n, where n is greater than or equal to 0. So it means it's optional, or there could be an arbitrary number.
Yeah, 1.1 state, right?
Yes.
Okay, yeah. There you go.
If you're going like this one, you have these, this one has that in here. You're adding these, then you need to add at least 2, then start.
So let's use our design from last time. We're gonna try to start at a single place and split into 2. So we'll start with an initial state, Q0. We want one branch out of this to solve the left-hand side. We have to be a little bit careful as we do this. It's really tempting to do something like this. On an A, we're gonna go to Q1, that's a final state because that's an odd number of A's, and then go back here on an A. So the idea would be 1, 2, 3, 4, 5, 6, 7. That works by itself to solve the left-hand side. Why don't we want to do this in this case?
So.
Can anyone see the upcoming issue?
You're doing some number of A's, you can then from Q0 move to.
Yes, if the idea is we're gonna have something out of here representing the right-hand side, like A. Q2, B. Q3, and then we want that to be a final state that loops to itself on an A. Now we can have A, B, which is not part of either language, and lead you to a final state. So how do we want to solve this? Yeah,
Take away the A from 0 to 2.
okay,
And have it go from Q1 to Q2. And then replace the A on Q3.
what's the symbol here?
That'd be A on B. We're gonna place the A on Q3 with the B. No, on
It's
Q5.
this,
No, keep both of those.
B here, A here,
No, B at the end.
and then a B here as well.
Let's B to the end, not A to the end.
The looped A needs to be a looped B. Above cubic.
To here.
Yeah.
Let's see, we want A, B, B to the end. So, yeah, A, B, so I did it wrong in the first place, it needs to be B.
Yep.
Does this work?
Q3 to loop back to Q2. It doesn't be.
No, because then Q2 has to be what's called end state, which would mean that you could do A, B.
How about A, B, B?
If you,
We would end up accepting that. Because there's a path, A, B, B, to a final state. So I think we do still want this on an A. But I think we need one more state out here that doesn't allow us to go back to Q0. So we're going to make this now, I guess, Q4 on an A, back on an A. And now there's no way to go between the left side and the right side.
That also worked if you had that, so the previous solution, that we just said didn't work.
As long as we didn't have the ability to teleport between, because they are so different. But do note that they both start with an A, but one of them has us accepting that first A, and one of us does not. So that tells us that there's already a difference between this. We're out of time for the day, but what we're gonna be covering tomorrow is the actual algorithm for converting an NFA to an equivalent DFA. Because that is an important thing for us to be able to do, to show that these are equivalent. Sometimes it's really easy to design an NFA solution, and it's really difficult to design a DFA solution. One way to design the DFA solution is make an NFA, convert that into a DFA following this conversion algorithm. So we will go over that, get some practice with it tomorrow. Questions on this while people pack up? Remember that you have a homework that is due on Wednesday. There's quite a bit to it, so I recommend getting started early, getting stuff early, getting help. We also have an exam a week from Friday. So I'm gonna get a study guide to you on Friday with the topics that that exam will cover. I will try to get your homework turned around within a day, so that you have a day to figure out, what did I do wrong in that homework, how can I learn from it before you take the exam? Questions, concerns? Great, I'll see you all tomorrow. Office hours starting down in my office, if there's anything I can do for you.